Good morning. My name is Bello Mary, a PhD student of the College of Nuclear Science and Technology, Harbin Engineering University, China. I'm going to be presenting a study on the effect of system parameters on the onset of flashing instability using RELAP5 code. First, the outline of the research. We have our introduction, objective, experimental facility that is adopted, RELAP5 nodalization used in the experiment, nodalization sensitivity, effect of inlet subcooling, effect of height of riser, effect of inlet resistance, which were the parameters studied, and then the conclusion. Introduction. Natural circulation systems, as we know. Natural circulation systems, as we know, are prone to instabilities, mainly due to the low driving head and non-linearity of the system. Instabilities can lead to a lot of situations in the system, which is not limited to mechanical damage of the system, power fluctuation, operational problem in control system, premature critical heat flows, which can cause burnout of the system. Looking at our main point, flashing. This is the sudden vaporization of fluid due to a reduction of pressure. It occurs due to the presence of nucleation sites along the wall of the system. Also occurs when temperature at the inlet is equal to or higher than saturated temperature at outlet. It increases with decrease in pressure. That means with a decrease in pressure, the flashing instability increase. The process is schematically illustrated in figure 1, as you can see, where the inlet temperature equals the saturation temperature, and we have flashing in figure 1. Now, looking at some work that has been done in flashing before now, some researchers have carried out experiments on flashing to see how it affects the system and its work. We have Shao et al. In 2020, which carried out flashing induced instability in the natural circulation system, and they observed various oscillation patterns resulting from the flashing instability of the system. Go et al. 2015 also observed oscillation behavior resulting from flashing and how this changed the system parameters affecting the instability. Lakshman and Pandan in 2009 noted that flashing instability was one of the oscillations observed in the startup of its test facility and its natural circulation reactor prototype. Sheehan in 2005, going back further, we have employed track code in analyzing the startup procedure of ESBWR, which is a type of boiling water reactor system, and observed that the main instability at the startup was flashing instability. Now going to the study for today. We have the objective study was to find the point at which flashing begins, inception of flashing at the different parameters studied, and to study how the various parameters affect the inception of flashing and the effect on the system as a whole. Now, looking at the experimental facility. The experimental facility is a novel modular reactor with an electric output of 50 megawatt electric. The schematics and the facility and instrumentation of the experimental facility can be found in the work of Shield et al. Of 2015, where the various system parameters and everything used to carry out the experiment was discussed at length. So this is what we adopted in our RELAP nodalization. Now, RELAP5 nodalization, we have various pipes and branches used to represent the various parts of the system for our own study of the experimental facility. Now, it has been observed by various authors that nodalization system is actually sensitive to different factors, and we decided to study the effect of using different number of volumes in each of the pipes to represent the core, the riser, and the diaphragm, and observe the result obtained for each of the nodalization. We have 3 different nodalization that were observed with different volume for each of the core parameter, core component, the core, the riser, and the diaphragm. And in this study, we discovered that the nodalization sensitivity for the various number of volumes gave similar results. So to save time for time and accuracy, we decided to use the nodalization scheme with the lowest number of volumes, which is nodalization 1. It gave the equivalent result to the others, and we decided to adopt it in our study. Also, we observe from which other authors have also carried out research on that oscillations at different pressures were affected by the pressure of the system. So we discovered that flashing is suppressed at higher pressures, and because of the study we wanted to carry out, we decided to use a lower pressure where we can study the effect of flashing effectively. And for this study, all the experiments were carried out at a pressure of 200 kilopascal, where the effect of flashing can be very much observed. Now, going to the parameters studied, we have the inlet subcooling, we have the height of riser, and we have the inlet resistance. But we are starting with the effect of inlet subcooling on the onset of flashing and on the working of the system as a whole. The first condition studied under the effect of inlet subcooling is when the inlet subcooling is 10 Kelvin. As I said earlier, pressure is maintained at 200 kilopascal and different heat flushes of 40 kilowatt per meter square and 20 kilowatt per meter square. Result of this experiment is shown in figure 7, and we discovered that the onset of flashing was at the inlet of the riser for both heat flushes. In figure 7, we can see that the onset of flashing was at the inlet of the riser. From the diagram, we saw the length of the heater to 1.1 meters, and then remaining is the length of the riser, and we discovered that the onset of flashing in this particular first condition was at the inlet of the riser. Now, looking at other condition, which is at 20 Kelvin, inlet subcooling of 20 Kelvin, still maintaining the same pressure of 200 kilopascal and heat flushes of 40 kilowatt and 20 kilowatt. We discovered that the onset of flashing moved upwards towards the center of the, as shown in figure 8, where the onset of the flashing moved to the center of the riser. The third condition observed under effect of inlet subcooling was inlet subcooling of 30 Kelvin, still maintaining a pressure of 20 kilopascal for all the conditions, and then heat flushes. Now, heat flushes of 40 kilowatt and 50 kilowatt, so that we can see the effect clearly at inlet subcooling of 30 kilowatt. And the result obtained is shown in figure 9, where the onset of flashing moved to the outlet of the riser. Now, what observation for this particular condition? The observation is that inlet subcooling affect the point of inception of flashing, and as inlet subcooling increased, onset of flashing moved to the outlet of the riser. What is the effect of this on the system? We'll be coming back to that even as we check the effect of other parameters on the flashing stability and the operation of the system. Looking at the effect of height of riser flashing inlet riser. Now we move to the second condition we studied, which was the riser height of 6.5 meters, and the result is shown in figure 11, where we discover the section of flashing moved upward toward the center of the riser. If you are observant, you will notice that this is similar to what we observed in the inlet subcooling on the effect on its effect on section of flash. Now, at the third condition for the effect of height of riser, which is riser height of 8.5 meter. Result is shown in figure 12, and we discover that the onset of flashing moved to the outlet of the riser. Now, for this particular condition, boiling was suppressed at the outlet of the heater. Why? Due to an increase in the hydrostatic pressure being built up as a result of the steady rise in the height of the riser. Now, this is what you observe for the third condition of riser height of 8.5 meter. Now, before we sum up all our observation, we moved observation for this particular parameter, which is the height of the riser. We discover that onset of flashing moved to the outlet of the riser as the height increased and boiling is suppressed. This shows that the effect of flashing becomes more pronounced as the length of the riser increases. Other authors like Shaman and Pardin in 2009 observed the same trend in their experiment. Now, going to the last parameter studied, which is the effect of inlet resistance on the flashing instability on the system. For this particular parameter, all conditions were studied at heat flux of 40 kilowatt per meter square and inlet subcooling of 30 Kelvin. Now, the first condition was inlet resistance of 10, when the inlet resistance of the system was maintained at 10, and the results showed in figure 13. Onset of flashing was towards the center of, as you can see in figure 13. Now, moving to the condition observed, we have inlet resistance of 50, and figure 14 shows the result of onset of flashing occurring at the inlet of flash of the riser. Same observation for the third condition, which was inlet resistance of 100, where the onset of flashing moved also to the inlet of the riser. So this tells us that the onset of flashing moved to the inlet of riser with an increase in the inlet resistance, as seen with the inlet resistance of 50 and 100 in the figures above. This was also observed by Marcel et al. In 2009 in the experiment they carried out on the Circus facility. Wrapping all this together, in conclusion, you can see effect of system parameters studied in this work, including the inlet subcooling, height of riser, inlet resistance, on the onset of flashing were dependent on the particular parameter being considered. While for an increase in inlet subcooling and height of riser, the flashing moved to the outlet of the riser, it stabilized the system, while an opposite effect was observed with an increase in the inlet resistance. Now, further work that can be carried out is in observing other parameters too, how the change of conditions for the other system parameters will affect the onset of flashing, and also how flashing and boiling intertwine, how they operate together in all these conditions. Those are other studies that will be carried out in the future to have a broader perspective and conclusion on the definite effects of these parameters on the various, on the onset of flashing, inception of flashing on the system, and how it affects the operation of the system. Thank you very much for your time.